Okay, so let's go ahead and get started on today's lesson, which is on collision types. This is in section 6.3 of your book, and it's going to deal with elastic and inelastic collisions. So this diagram is not from your book, but it does show a situation where some balls are approaching each other and they're going to collide. And they can collide in two ways. One way is called an elastic collision, and another way is called an inelastic collision. And I just want you to consider these three questions over here on the right-hand side, and just try to answer these yourself before I go through them. What's different between the two cases? What's the same? Is momentum conserved, and how does the diagram show it? And is kinetic energy conserved, and how does the diagram show this? So let's go ahead and take a look at this first one. So what's different between the two cases, and what is the same? What we can see is that, first, what's different? In the inelastic collision, it has less speed after the collision between these two. So in the elastic collision, we have more speed after the collision, and in the inelastic, we have less speed. But what's the same is that VA is always equal to VB in each case. So the actual speeds of each of these objects, VA and VB, they're the same in either case. We have the exact same speeds coming out of the collision in this case as well as in this case. So they are identical speeds. They're just, in this case here, they're the same as the speeds as they were coming in. In this case, they're less. Now that helps us understand momentum. Is momentum conserved? And the answer is yes, it is conserved in either of these cases. In both cases, the initial momentum, if these are equal mass balls and they're moving with equal speeds, the total momentum is 0 in each case. And that's the case regardless of whether or not it's an elastic collision or an inelastic collision. And then the last question, is kinetic energy conserved? And you should see that kinetic energy is only conserved in the elastic collision. And that's really the defining characteristic for elastic collisions, is whether or not kinetic energy is conserved. So we say that a collision is elastic if kinetic energy is conserved. Elastic and inelastic collisions always conserve momentum. So we always get momentum conservation, but we only get kinetic energy conservation when we have an elastic collision. Now I'd like to show you that with this simulation. This is from PhET, and this is just a couple of balls that are going to be approaching each other, and I've got the elasticity mark over here set at 100%. We have a momentum diagram down here to the right-hand side, and then we have some velocity vectors. Let's go ahead and play this. You can see they hit each other and they bounce off, and when they do, you can see that the momentum diagram, I'm going to go ahead and try that one more time. So right before they hit, we have momentum of 1, momentum of 2 in opposite directions. The total momentum is 0. And then after they hit, we see that essentially the two objects change their momentum equally, and we still have 0 total momentum. And we also have no change in kinetic energy. I'm going to go ahead and show the kinetic energy value there, restart that. And as I play that, you can see that when they hit and bounce off each other, the kinetic energy retains. It stays the same. Now if I start to change the elasticity, let's say that these aren't perfectly elastic, and they go ahead and they're going to bounce off each other. Again, you can see we have the momentum diagram is showing that the total momentum is still 0. We go ahead and let these things hit. We can see that first off we lost some kinetic energy, but we still have 0 total momentum. Each of the objects has less momentum than they had beforehand, but they still add to 0. So momentum is always conserved. Kinetic energy is not always conserved. Let's go ahead and make this an extreme case. Let's go ahead and make it be 0% elastic. So when these objects hit and collide, what do you think is going to happen to the kinetic energy? They do have equal but opposite momentum. Are you ready? Let's see if you predicted correctly. And sure enough, all of the kinetic energy is gone. These two objects hit and completely stuck together, which means that they've lost all their kinetic energy, but we still have the same momentum as what we started with, which turns out to be 0. Now this is from your book, this table. This is showing what happens in 3 different kinds of collisions. We got the perfectly inelastic, we have the elastic, and then the inelastic collisions. Momentum is always conserved in the perfectly inelastic. Momentum and kinetic energy is conserved in the elastic, and momentum is conserved in the inelastic. Now probably the biggest thing that we need to look at here is the difference between perfectly inelastic and inelastic. These two are not the exact same thing. What happens, a perfectly inelastic collision just means that they stick together, that they actually, this is what we used to call the hit and stick, or what we called the hit and stick in the last section. So when objects hit and stick together, that's actually what we would call a perfectly inelastic collision. Now, in a situation like this, the inelastic collision, the objects hit, they bounce off each other, they don't end up retaining their initial kinetic energy. You can see that kinetic energy is not conserved. And if you look really closely here, I'm going to have you take a look at the actual deformation that occurs in those balls. Some of the energy went into deforming those balls that didn't come back out, it didn't return to its original shape, and so we didn't really store any elastic potential energy in that deformation. Whereas up here, we actually did store energy in that deformation, and we got the energy right back out. So again, we have a little bit more scientific way of describing collisions now. Instead of hit and stick and hit and rebound, we can actually call them elastic, inelastic, or perfectly inelastic, depending on whether or not kinetic energy is conserved. So how is perfectly inelastic different than inelastic? just whether or not they are sticking together. And perfectly inelastic collision is most similar to the hit and stick that we studied in the last section. Now I have a variety of examples I want to go through with you. These are just showing you how to use the conservation of momentum equations, and also how to look at conservation of kinetic energy if we actually had an elastic collision. So let's go ahead and just draw a quick picture here. 1,800 kilogram car moving 4.2 meters per second towards the east, so let's just draw a quick picture here. So it's moving this way at 4.2 meters per second, and it's 1,800 kilograms. So from that we can determine the object's momentum. So it's an 1,800 kilogram car moving that way. It collides head-on with a 1,400 kilogram car moving towards the west. So it's a little bit smaller car. It's moving in the opposite direction with a greater speed. So 5.6 meters per second, and its mass is 1,400 kilograms. Now from that we have two objects, each with momentum, and what we'd like to do is determine what happens when the two cars hit, and they do stick together. So this would be called a perfectly inelastic collision. What is the velocity of two cars immediately after the impact? Well, we're going to start this just like we did before. We're going to say that the total momentum stays the same during this collision. So P initial is equal to P final. Let's write that as so. In the beginning, we have M1 V1 plus M2 V2, and that's going to end up going to, since they stick together, we're going to go ahead and say that that's M1 plus M2 times V2, or times V final rather. Now I have all of these numbers here except for V final, and that's what we're looking for, is what is the velocity after the collision. So let's just go ahead and solve this equation for V final. I'm going to switch sides here. V final is just equal to M1 V1 plus M2 V2 all over the sum of those masses, so all over M1 plus M2. I'm going to go ahead and just give you the answer there so that we can keep moving on. Okay, so let's go ahead and just plug in some of those numbers here. That's 1,800 kilograms. I'm going to drop the units for a little bit of time here. 1,800 times 4.2. Now that's towards the east, so I'm going to call that the positive direction. Now I do have to be very careful about this next one here. I've got to subtract away the momentum of the other car since it's moving in what we would call the negative direction. I'm going to go ahead and make that be a negative value, and that's important to make sure that we get the proper sign for our total momentum. Now M1 plus M2, 1,800 plus 1,400 looks to be about 3,200 kilograms. And with going through this calculation, I should be able to calculate what the final velocity is. So let's do that now. We see that the numerator is a negative 280 kilogram meters per second, which essentially means the car moving towards the west or in the negative direction had the greater momentum. And so when I divide that by the total mass of 3,200 kilograms, we get an overall velocity, very small. V final is about a negative 0.088 meters per second. So it's mostly come to a stop. So this would be a situation where both cars had almost the same momentum as they were coming into the collision. The 1,400 kilogram car had a little bit more. When they hit, they would actually end up moving this way with a very small speed. We've lost a tremendous amount of kinetic energy because this is a perfectly inelastic collision. So if we want to determine how much KE was converted, what we would do is we would just determine KE initial, and then we would also determine KE final. Now, since kinetic energy, how does it compare? It's going to end up being, KE initial is going to be quite a bit greater than KE final. But we want to be able to determine what those values are. So since each object is moving separately in the beginning, I would end up calculating this by going 1/2 M1 V1 squared. And since these are scalar quantities, I wouldn't have these two sort of reduce each other like we had for momentum. These are going to end up being positive values only. So when we go ahead and compute these, I'm just going to stop this and give you what those numbers are. 1/2 1,800 times 4.2 squared, and then 1/2 1,400 times 5.6 squared. Let's go ahead and compute that quick. Okay, this first one is 15,876 joules, and the second one is 21,952 joules. So we can add those up together, and we get that the total energy before the collision is about 37,828. And if we were to round that to sig figs, that'd be probably about 38,000 joules. Now, after the collision, what we have is both masses combined. So that would be 1/2. That's 3,200 kilograms is the total mass. And they're moving at a very slow speed right after the collision, 0.088 meters per second. And so when we take a look at that value for the final kinetic energy, we get only about 12 joules, maybe about 12.4 joules. So most of that energy is gone. Where it's gone is into deforming the cars, not getting any of that energy back out. They're not elastic bumpers or anything like that. And so most of the energy went into deforming the cars. Intense heat, intense sound, and so we've ended up losing a tremendous amount of KE. Now, we didn't lose energy as a whole. Energy as a whole is still conserved. It's just gone into non-mechanical forms. Let's go ahead and take a look at another couple of examples. This is one that we will do in class. It's a ballistic pendulum. Just as an old-fashioned way of being able to calculate the speed of something moving really fast, like back in the early days before they had high-tech radar detectors and so forth to determine speeds of bullets. They would fire a bullet into a block of wood and then have it rise a certain height, and then measure from measuring how high the block actually rose after the bullet embedded itself into that block, we could determine then the speed of that bullet. I'm going to go ahead and show you how to do this. So we have a 75-gram bullet fired from a gun horizontally into a block of wood that has a mass of 6.5 kilograms. It's hung from a cord as a pendulum. The bullet embeds into the wood and the combined mass swings to a height of 17.5 centimeters above the equilibrium position of the pendulum. That distance here is actually easy to measure. It's just how high does it rise. It's very difficult for us to measure that speed directly, but we can work backwards to figure out how fast it was going by measuring something like the height, which is very easy to measure. So the way I'm going to do this is it's really a two-part problem. The first part is I'm going to use conservation of mechanical energy that has occurred after the collision. MEI is equal to MEF. This is the idea that mechanical energy is conserved during this process. So once the bullet embeds itself in the block, whatever kinetic energy it still has is going to get converted into gravitational potential energy. So this is all right after the collision, not during the collision. During the collision, we don't have mechanical energy conserved. So this is after the collision, where whatever mechanical energy we still have is conserved as it rises up and changes from KE into GPE. So it's the initial kinetic energy, and that would be the kinetic energy. I'm going to go ahead and put AC here for after collision. Ends up going to GPE after the collision. And so, and that's again to make sure that we don't try to do this with anything before the collision. So that would be 1/2 the total mass. So I'm going to write M total times V after the collision squared. Ends up going to mass total, the total mass, times G, times change in height, and the height is how high it rose. Now at this point, you can see that the mass of the total mass cancels out, and if I want to determine the speed of the bullet and block right after the collision, that's simply done by just saying that VAC is equal to the square root of 2GH. And in this case, I'm given all this information. I can go ahead and calculate the velocity after the collision. So 2 times 9.8 meters per second squared, multiplied by the change in height that the pendulum went through, which was 0.175 meters. So let's compute that quick. And that value turns out to be about 1.85 meters per second. So that would be the speed that the bullet and block acquired after the collision. That's not the speed of the bullet. Certainly that's not. That's quite a bit slower than the speed of the bullet, because we now have a lot more mass moving after the bullet has collided. Now, the interesting thing about this is that momentum is conserved during this portion. It's not conserved after the bullet embeds and it starts to rise. There we have gravity acting and so forth, so momentum eventually goes to zero, and we've stored some of that kinetic energy into gravitational potential energy. But here, what we've got is momentum transferred from one object to the next, and momentum is conserved here. So we're going to go ahead and do the second part. So second is that we're going to use the conservation of mechanical energy. The conservation of momentum. So the initial momentum ends up going to the final momentum. They end up equaling each other. Before the collision, we had only the mass of the bullet moving. So I'm going to say velocity of the bullet, mass of the bullet, velocity of the bullet, initial. Ends up going to, it's a hit and stick or a perfectly inelastic collision. So that ends up going to the mass of the bullet plus the mass of the wood times V after the collision. Now I've already calculated V after the collision. It's right down here. So I can take that value and plug that into this equation to find the velocity of the bullet. So the velocity of the bullet initial is just equal to, let's see, the total mass is 6.5 kilograms plus 0.075. So that'd be 6.575 kilograms. That would be the entire mass of the bullet and the block. It's moving at 1.85 meters per second. That's how fast it came out of that collision. And when I divide that by the mass of the bullet, which is what I'm doing here, I'm going to make sure that that mass of the bullet is in kilograms. So that would be 0.075 kilograms. What I'll get then is the actual speed of that bullet prior to the collision, which is what I was interested in. Let's go ahead and do that. And I get about 162 meters per second. And again, I could round that to maybe 160. It looks like maybe 162 is about right. But that would be the way in which I would use two laws, the conservation of mechanical energy and the conservation of momentum, in order to determine the speed of that bullet. Now, how much KE was converted to other forms during that collision? I do the same thing that I did before. I just take 1/2 the mass of the bullet, the velocity of the bullet before the collision, squared, and that was the only thing that was moving. Afterwards, what I had was 1/2 the total mass times the velocity after the collision. And what we'll see here is, again, a tremendous amount of kinetic energy that's lost. So 1/2, the only thing moving in the beginning was the 75 gram bullet, and it was moving at 162 meters per second. And so when I compute that kinetic energy, I get about 984 joules. So a lot of kinetic energy in that fast-moving bullet. And then when I compute the kinetic energy of the system afterwards, I get a much smaller number. Let's go ahead and just see what that is. 1/2 of 6.575 kilograms. Its velocity after the collision is only 1.85 meters per second. So it's going to be quite a bit smaller since I'm squaring that. And what we get is only about 11 joules. So 11.3 joules or so. Again, we've lost a tremendous amount of kinetic energy there. How much Ke was converted into other forms, I would take the difference between these to be able to do that. So we've lost essentially almost all of the kinetic energy. Now this is one that we'll do in class. I'm going to save that for a classroom demonstration. And finally, this is an interesting application of conservation of momentum to be able to reconstruct an accident scene. So I want to go through this one in detail with you and show you how we use both conservation of momentum and the work kinetic energy theorem. This is using a little bit of friction here. We're going to use the relationship between frictional force and normal force that we studied back in chapter 4 to be able to work backwards through an accident scene and figure out the speed of a car coming in to a collision. So we're going to make this a simple one-dimensional collision with only one car moving. We have a 1,700 kilogram car that slams into a 1,400 kilogram car that's stopped. So here I have a 1,400 kilogram car. It's at rest at a stoplight, and I have another car coming in. And that car is coming in at some unknown speed, and I want to determine what that is. So I'm going to call that V initial. And again, I have some masses here, so 1,700 kilogram car, 1,400 kilogram car. They end up hitting. And during that hit, when the two cars sort of stick together, what we know is that the momentum is conserved. So Pi is equal to Pf, but the kinetic energy is not conserved. So Ke is lost during that collision. Now, when they slide, Ke is lost, but we still do have some kinetic energy. Kinetic energy after the collision is quite a bit smaller than what we had before the collision, because we did lose a lot there. But whatever kinetic energy we have ends up going to zero as these two objects slide to a stop after traveling some distance. So they're going to slide to some stop a distance away. And based on measuring that scene, these cars do not look the best there, but based on measuring that distance, which turns out to be 3.2 meters, we can go ahead and use an idea here. We're going to use the work is equal to delta Ke theorem to be able to study this. So what we're going to do is we're going to use conservation of momentum to analyze the collision, and then we're going to use work kinetic energy theorem to analyze or to determine things like the kinetic energy that they had right after the collision. Let's go ahead and start this by working at the end of the problem first and working back this way. So let's first start with the work kinetic energy theorem. Now, in this case here, we did lose kinetic energy, but we still do have some kinetic energy present. Our goal here is to try to determine what the speed is after the collision. So I'm going to use the net work. Net work is equal to delta Ke theorem to be able to determine the speed right after the collision. Now, in contrast to the ballistic pendulum idea, I use the mechanical energy conservation law to be able to find the speed after the collision. Here, since I have frictional forces acting, I don't conserve mechanical energy, but I can use the work is equal to change in Ke theorem. So the work is done by friction, so it's going to be F sub K times D, how far it slid. Now that's negative work because the force of friction acts in the opposite direction of the way that the object is moving. And it ends up going to zero kinetic energy, but it started at 1/2 m, and that's the total mass, so both cars have combined, times the velocity after the collision, which is what I'm looking for. And so what I'm looking for in this particular problem is VAC. So I'm just going to go ahead and solve that now for VAC. Before I do that, I should probably replace the frictional force with mu times the normal force. So let's go ahead and do that. This might, you may have forgotten this, but we take the frictional force as mu times F sub n, where the normal force in this case would be equal to the weight of the object. You can see I'm going to drop that negative sign there and that negative there. And so I get 1/2 the total mass times VAC squared. Now, since the normal force is equal to the weight of the object, I can go ahead and replace F sub n with the total mass times G. And then I still have that D there is equal to 1/2 the total mass times the velocity after the collision squared. And again, as is common, we see that the mass does end up reducing out here. I don't need to know what the masses of those cars are to solve this part of the problem. Since I'm looking for the velocity after the collision, I'm going to go ahead and multiply both sides by 2 and then take the square root. So what I get is 2 u sub k times g times d is equal to VAC squared. And since I'm looking for VAC, I'm going to go ahead and take the square root of both sides. So this allows me to calculate what the velocity is right after the collision by using something that we learned back in chapter 4. Let's go ahead and compute that. And what we get for that value is about 6.7 meters per second. So again, we were able to figure this out by looking only at the accident scene. By measuring just the distance that the cars slid and the coefficient of friction, I was able to determine what the velocity was right after the collision, just using the work kinetic energy theorem. Now the next part, this is where I'm going to be able to use conservation of momentum to be able to determine the initial speed of that car coming in. So I'm really using two key physics principles, work kinetic energy and conservation of momentum. Now this is a hit and stick collision, so again I'm going to start, let me actually start that with this statement. The total momentum before the collision is equal to the total momentum after the collision. Before the collision, the only car moving was M1, the car coming in. So M1V1. That ends up going to the total mass. I'm going to say M1 plus M2 times the velocity after the collision. And we computed that in the previous portion. So now since I'm looking for V1, the velocity of the car, I can just take that to be M1 plus M2 multiplied by VAC, and that I computed before, all divided by the mass of car 1. So let's go ahead and compute that. And what I get for that value is about 12.2 meters per second, which is about 25 miles per hour. And so an accident investigator could come out and look at this and say, basically come up with the speed that car came in and hit that car at. Now, if this were a 25 mile an hour speed zone, then it might tell the accident investigator that the person maybe was not speeding, but they just weren't paying attention, and they slammed into the back of that car. If it were a faster speed zone, like maybe a 45 mile an hour speed zone, maybe the person had braked ahead of time, but still had a lot of speed coming in and hitting that car. So again, additional information that can be determined by looking just at the accident scene and working backwards using some fundamental physics ideas. Now, we'll take a look at this one here where we look at collisions at right angles, but we'll do that one in class. I'm going to go ahead and stop it there, and we'll see you in class. Go Bucks.